Your eyes save your life. You don't fall down stairs. You don't eat spoiled food. You dodge cars in traffic. Your intuition whispers. You survive because you see reality as it truly is. It sounds reasonable. If your ancestors hallucinated instead of seeing a lion, they would have been eaten. So evolution must favor those who see the truth. This feels obvious, and it is completely wrong. There exists a rigorous scientific theorem, proven mathematically, that states the opposite. Evolution does not reward organisms that see true reality. It ruthlessly eliminates them. Creatures that perceive the world as it actually is consistently lose to those who see only what is necessary for survival and the transmission of genes. Truth is not an advantage. Efficiency is. Consider a simple example. Turn on your computer and look at your desktop. You see a yellow folder in the center of the screen. Does this mean there is literally a small yellow rectangle inside your computer? Of course not. The folder is an unimaginably complex pattern of zeros and ones stored on a physical medium. The icon bears no resemblance whatsoever to what is really happening inside the machine, and that is precisely the point. If you had to manipulate voltages, magnetic domains, and raw binary data every time you wanted to open a file, you would lose your mind. The icon hides the overwhelming truth and presents a simplified interface that allows you to act. Evolution has done exactly the same thing to us. Space and time are our desktop. Physical objects are icons. A snake, an apple, a car, these are not reality itself. They are user-friendly symbols that conceal the true structure of the world so that we can make fast decisions, run, eat, reproduce. Knowing the truth is too costly, too slow, and too dangerous. You might ask, if a car is just an icon, why not step in front of it? An excellent question. For the same reason, you don't drag an important folder into the trash, not because you believe the folder is actually made of paper, but because you take the interface seriously. Actions performed on icons have real consequences. Delete the wrong files, and you lose your job. Step in front of a truck, and you die. The lesson is subtle but crucial. We must take our perceptions seriously, but not literally. Physicists increasingly confirm what we have long suspected. Space and time are not the bedrock of reality. They look more like a data format, a way information is packaged for us. Even your vision is a relentless exercise in saving resources. You feel as if you see the entire world in sharp detail. But this is an illusion. In reality, you perceive clarity only in a tiny spot, roughly the size of your extended thumbnail. Everything else is blurred and reconstructed by the brain. We literally create objects with our gaze when we need them and delete them when we look away, much like a video game engine that loads textures only where the player is looking. So, what exists beyond the screen? If space and matter are merely an interface, what is the processor underneath? This video draws on the books and interviews of Donald Hoffman. And if you're thinking, what could a psychologist possibly know about the nature of reality? Wait. Hoffman studies consciousness, perception, evolution, and attention using mathematics, experiments, and computer simulations. His work is rigorous and testable. His most famous book, The Case Against Reality, is often compared to the red pill from the Matrix. It invites us to remove the virtual reality headset evolution placed on us millions of years ago and to ask what objective reality might actually be. Now meet a man named Joe, an ordinary factory worker except for one detail. He has two brains, literally. Joe suffered from severe epilepsy, with seizures striking daily, sometimes several times a day. His life became unbearable. Eventually, surgeons made a radical decision. They severed the connection between the two hemispheres of his brain, cutting the corpus callosum, the massive neural cable through which the left and right halves communicate. The operation worked. The seizures stopped, and Joe returned to everyday life. But something strange followed. For more than 15 years, neuroscientist Michael Gazzaniga studied Joe, and what he discovered was astonishing. Try a simple experiment. Draw a circle with one hand and a square with the other at the same time. For most people, this is nearly impossible. The hemispheres interfere, signals collide, the hands refuse to cooperate. But Joe does it effortlessly. His hands act independently because they are controlled by two separate minds. Here's another experiment. Michael Gazzaniga shows Joe a word on a screen, but with a crucial trick. The word is presented to only one hemisphere at a time. If only the right eye sees it, the information goes to the left hemisphere. If only the left eye sees it, the word goes to the right hemisphere. When the word reaches the left hemisphere, Joe calmly reads it aloud This side controls speech. But when the word is shown to the right hemisphere, something unsettling happens. Joe says, "I didn't see anything." He is not pretending. He genuinely has no idea what was shown. Yet, if Gazzaniga places a pencil in Joe's left hand, controlled by the right hemisphere, Joe immediately draws the object he saw, a telephone. Then comes the most disturbing part. Gazzaniga shows the word bell to the right hemisphere and the word music to the left. He asks Joe to point to what he saw. Joe points to the bell using his left hand. "Why did you point to the bell?" Gazzaniga asks. And the left hemisphere, which saw only the word music and knows absolutely nothing about the bell, instantly invents an explanation. "Well, the last time I heard music was when the bells were ringing in the street." Do you see what just happened? The left hemisphere had no access to the real cause, but it cannot tolerate the absence of explanation. It is our inner storyteller. It immediately constructs a coherent narrative, even when it has no idea what actually occurred. Gazzaniga believed this to be a defining feature of the human mind. The left hemisphere is constantly searching for cause and effect. It explains, it interprets, it fills in gaps, even when it is wrong. This is an extraordinary evolutionary advantage. A species that relentlessly asks why and searches for patterns survives better than one that does not. But there is also the right hemisphere. It is silent, it cannot speak, yet it excels at visual recognition. Gazzaniga showed Joe paintings by Giuseppe Arcimboldo, a 16th century artist who composed faces out of fruits and vegetables. When the image was processed by the right hemisphere, Joe immediately saw a face. When the same image went to the left hemisphere, he saw only fruit. The right hemisphere specializes in faces. This is an ancient adaptation, rapidly recognizing a face, determining friend or foe, reading emotions, sensing intent is a matter of survival. It is fast, intuitive, and silent. But when it comes to what makes a person, the ability to reason, invent, explain, and interpret, the left hemisphere takes the lead. Joe lives an ordinary life. He works, communicates, jokes, and plans. In daily experience, he almost never notices that his brain is split. And yet scientists can clearly see it. Two minds coexisting in a single skull. Two distinct ways of perceiving the world. Two parallel streams of consciousness. And this inevitably raises a disturbing question. If Joe has two minds inside one head, then what exactly is happening inside each of us? Let's be honest. We are all like Joe. Our brains make countless decisions at levels completely inaccessible to consciousness, and only afterward present us with a polished narrative explaining why we did what we did and not something else. The story comes later. The choice was already made. We are used to believing that we possess a single, unified I, but science tells a far less comforting story. Your I is not a thing. It is a process, the result of connections between neurons. Sever those connections, and the I fractures. Consciousness can be divided with a scalpel, and perhaps this is one of the most unsettling discoveries ever made about human nature. What kind of beings are we if our beliefs, desires, personalities, and perhaps even the fate of our souls can be dissected with a scalpel? Why do we have consciousness? What is consciousness? Can neuroscience solve the eternal mystery of human consciousness? The spotlight of science, which has penetrated deep into the realm of the inanimate black holes, bound quarks, slow tectonic plates, is now focused on what matters most to us, our deeply personal world of conscious beliefs, desires, emotions, and sensory perceptions. Will we be able to catch even a glimpse or even comprehend ourselves? This is what the science of consciousness strives for. Science is a hunt. We are chasing the holy grail of consciousness. We hope that one day we will find the golden key that unlocks the mystery of the mind, just as the discovery of DNA once unlocked the mystery of life. And we already have important clues. We know for certain that what happens inside your head is tightly coupled to what you experience. Change the brain, and the world you perceive changes with it. Take color. There is a specific region of the brain known as V4. When a person suffers a stroke in this area, the world becomes partially colorless. A red apple may appear red on one side of the visual field and gray on the other. Even more unsettling, this system can be manipulated like a switch. Using magnetic stimulation, scientists can temporarily deactivate this region. Place a special magnet on the head, colors fade. Remove it, colors return. We can quite literally turn parts of perception on and off. Or take touch. In the 1930s, neurosurgeon Wilder Penfield applied electrodes directly to the exposed brains of patients and mapped the human body onto the cortex. What he discovered was bizarre. Body parts were arranged in unexpected ways. Toes located near the genitals, hands disproportionately large. Perhaps that curious wiring explains why some people find foot massages so intensely pleasurable. Today, our tools are even more powerful. We can directly intervene in emotions themselves. Certain fears, such as arachnophobia, are linked to activity in specific brain structures. A therapist can deliberately activate the fear by asking a patient to touch a live tarantula and then administer a drug that erases the emotional association. The therapy works. The fear vanishes. And in animals, the manipulation goes even further. With a technology called Optogenetics, scientists insert light-sensitive genes into neurons, shine a laser into a mouse's brain, and you can forcibly activate happiness. The mouse may be sitting in a cold, frightening cage, but flip the switch, and subjectively, it is in paradise. But here is the irony. We know how to switch emotions on and off. We can see neurons firing. We can map circuits, stimulate regions, silence others. And yet, we have absolutely no idea how matter turns into feeling. We do not have a single equation that explains why activity in one group of cells becomes the taste of a banana, while activity in another becomes the sound of a siren. Why does a banana not taste like coffee? We have precise laws describing black holes and quarks, but no law for the taste of a banana. Perhaps we simply lack data, and we are waiting for our Einstein of neurobiology. Or perhaps we are like cats trying to understand quantum physics, not because quantum physics is wrong, but because evolution never designed cats to grasp it. But there is a third possibility. Maybe we are smart enough. Maybe the problem is not our intelligence, but the angle from which we are looking. We are deeply convinced of one thing. I see the world as it really is. You look at tomatoes and are certain that even if you close your eyes or turn away, they will still be there. It feels obvious, self-evident. But let's test that sense of reality. Look at the Necker cube. It is nothing more than lines on a flat surface, yet your brain constructs a three-dimensional object from them. Sometimes edge A is in front, sometimes edge B. The drawing never changes, only your perception does. Turn away, and there is no cube on the page at all. There is only ink. The cube exists only in your brain. The same is true of a tomato, just in a far more complex way. Galileo Galilei was the first to suspect this. He argued that color, taste, and smell do not exist in objects themselves, they exist in us. A tomato does not contain redness. It absorbs most wavelengths of light and reflects one around 700 nanometers. That wave hits your retina, triggers electrical impulses, and somewhere in neural networks, the sensation of red is constructed. The wave itself is not red. It is nothing but a fluctuation of the electromagnetic field. Redness is created by the brain. Galileo, however, stopped halfway. He still believed that the tomato's shape and position existed objectively, and that final assumption may be the last illusion we have yet to let go. But evolution disagrees. Evolution, by natural selection, implies a paradoxical theorem. The probability that we see reality as it is zero. This theorem applies not only to taste, smell, and color, but also to shape, location, mass, and speed, even to space and time. We do not see true reality. The reality that prompts you to create the experience of a tomato. The reality that exists independently of whether you see the tomato or not, is not at all like what you see and taste. We rejected the flat earth and the geocentric universe. We realized that our perception had misled us, and we corrected our mistakes. It wasn't easy. In the process, everyday intuition and church doctrines were shaken. But these corrections are just a warm-up. Now, we must throw space-time itself and everything in it overboard. We are used to thinking of beauty as something sublime. Poets write verses about it. Artists dedicate their lives to capturing it. David Hume famously said that beauty exists in the eye of the beholder. But he never explained why it ended up there in the first place. Where did this sense come from? Why does it exist at all? Charles Darwin gave an answer, and it is brutally cynical. Beauty is not an abstraction. It is a calculator. When you look at someone and feel admiration, your brain is running a cold, unconscious computation. It is estimating probabilities. Will this body survive? Will it resist disease? Will it produce healthy offspring? What you experience as beauty is the output of that calculation, dressed up by culture, poetry, and illusion. The predictions of evolution about beauty are amazing, but its predictions about physical objects are confusing. Objects, like beauty, are in the eye of the beholder and inform us about fitness, not about objective reality. Australia is home to the jewel beetle. The males of this species are irresistibly attracted to large, shiny females, brown in color, with distinctive bumps on their backs. One day, humans began discarding empty beer bottles into the desert. They were brown, they were shiny, and they had ridges at the base. You can probably guess what happened next. To the beetles, these were not bottles. They were super females. The males abandoned real mates and swarmed toward the glass. They attempted to copulate with the bottles until they were completely exhausted. They ignored the scorching heat. They ignored the ants that crawled up and began eating them alive while they were still making love to the glass. The population nearly collapsed until beer manufacturers changed the bottle design. Do you think we are smarter than these beetles? Not really, because our brains operate on the same fundamental principle. We, too, are driven by unconscious pattern recognition. We scan for signals of health, youth, and reproductive potential even when we have no idea that we are doing it. Take the limbo ring as an example. It is the dark rim around the iris, where the color of the eye transitions into the white. With age or illness, this ring fades and eventually disappears. A clear, dark limbo ring is a powerful biological signal. I am young, I am healthy, my genes are strong. Scientists tested this by showing people identical faces, digitally altering only the limbo ring, and the result was universal. Men and women alike consistently preferred faces with a darker rim without knowing why. We don't understand our preference, but something ancient inside us does, and it screams, "This is the right choice." But there is a dark side to this system. If beauty is a code, then it can be hacked. And in nature, a brutal hacker war has been going on for millions of years. Genes are willing to use any deception necessary to survive. There is an orchid that looks and smells exactly like a female wasp. A male wasp sees it, is overwhelmed with desire, and attempts to mate with the flower. Of course, there is no sex, only wasted energy. But the orchid gains a free courier for its pollen. The story of fireflies is even more disturbing. Males of one species flash a precise light code to attract a mate. Females of another species, larger, predatory, and far more dangerous, have cracked this code. They sit in the grass and flash back, "I'm here, come to me." The male flies in, full of hope, and is immediately eaten. The predator doesn't just get a meal. She absorbs toxic compounds from his body, making herself poisonous to birds. It is not just murder. It is the perfect crime. So beauty is the currency of evolution. Biologists sometimes call these fitness points. Your brain is constantly scanning the world, calculating, collecting, and spending them. Food, sex, safety, all of it is compressed into the single experience we label as beautiful. But, as the beetles and the beer bottle demonstrated, this code is not flawless. It can be exploited. Genes have no sense of fairness, no ethics, no morality. They do not care who is deceived, only whether replication succeeds. Think about what happens when you are extremely hungry. The smell of pizza feels divine. The first slice is pure bliss. Your body screams, "We are surviving, fitness points acquired." But after 5 or 6 slices, the very same smell becomes disgusting. Nothing about the pizza has changed. Nothing about the world has changed. Only your internal state has. The points are no longer accumulating. Beauty works the same way. It is not absolute. It is conditional, a moving target that shifts with what your genes need at any given moment. Try answering a simple question. What else in appearance signals youth? Here is a curious detail. In children, the colored part of the eye, the iris, appears disproportionately large. In older people, it looks smaller. Scientists have calculated that up to about the age of 50, the iris is objectively larger relative to the white of the eye. After that, the skin sags, the eye shape changes, and this proportion is lost. Men subconsciously prefer women with large irises. Why? Because a large iris equals youth, and youth equals fertility. A woman at 20 is almost guaranteed to be able to give birth. At 50, the probability approaches zero. A man who falls in love with a 50-year-old may live a long and happy life, but his genes will die with him. The genes of those who choose younger partners will not. That is why men are biologically programmed to be captivated by large eyes. This also explains why in Japanese anime girls often have eyes that take up half their faces. Artists intuitively discovered this attractiveness button long before scientists explained it. But what about women? Here, things are far more complex. There is a rigid rule in nature. The one who invests more in offspring gets to choose. A woman carries a child for 9 months and feeds it afterward. A man can limit his investment to minutes. That is why women are selective and men are persistent. But women face a genetic dilemma. On one hand, they need a reliable partner with resources, often an older man with status and wealth, but lower testosterone. On the other hand, they need strong, healthy genes typically found in dominant, high testosterone bad boys, who are often poor long-term partners. What did female genes do? They found a cunning solution. A woman's preferences shift throughout the month. During ovulation, when fertility peaks, attraction shifts toward high testosterone men. On other days, preference returns to caring, reliable partners. From the perspective of genes, this is the perfect strategy. Conceive with excellent genetics, raise the child with a dependable father. And there is one more detail about the eyes, the pupils. Pupils dilate not only in low light, but also when we are interested or aroused. When a woman looks at someone she likes, her pupils widen. The male brain reads this instantly. Interest detected. Scientists tested this directly. Men were shown 2 book covers with the same woman. The only difference was that in one image, her pupils were digitally enlarged. The result was overwhelming. Men consistently chose the book with the big-eyed woman without understanding why. They didn't consciously notice the pupils. They simply felt, she's looking at me. So when we fall in love, we should remember, this is not just romance. It is our ancient genes playing a long and ruthless game of chess, calculating moves not days or years ahead, but generations. And our feelings are merely pieces on that board. Scientists demonstrated this vividly in another experiment. Men were shown 2 photographs of the same woman. In one image, her pupils were very large. In the other, they were small. However, there was a twist. In the photograph with smaller pupils, the woman appeared younger, and the men split almost evenly. Some chose youth, others chose availability. In other words, evolution, that deeply cunning force, has not settled on a single optimal strategy. It has produced multiple competing strategies, each capable of winning under different conditions. This alone tells us something important. What we experience as a clear, confident feeling, I like her, she attracts me, this is my type, is in reality the surface manifestation of an ancient statistical algorithm. Genes do not seek truth, happiness, or even love. They seek replication, and they are perfectly willing to hedge their bets. Sometimes they prioritize fertility, sometimes accessibility, sometimes long-term investment, sometimes short-term opportunity. The internal conflicts we experience, attraction mixed with doubt, desire mixed with restraint, are not psychological accidents. They are evolutionary compromises playing out inside the skull. Now look carefully at another detail, the white of the eye, the sclera. Have you ever noticed how strikingly white it is in humans? This is deeply unusual. No other primate has eyes like ours. Monkeys and apes have dark sclerae, making it difficult for predators or rivals to tell where they are looking. So why did humans evolve eyes that openly reveal gaze direction? The sclera, or white of the eye, also affects attractiveness. No other primates have white sclera. Their sclera is dark, designed to hide the direction of their gaze from predators and from members of their own species, for whom a direct gaze can be threatening. The white sclera of the human eye reveals the direction of the gaze, making it a tool for social communication. It also shows emotions and health. The sclera is covered with conjunctiva, which is transparent and can be colored. The white sclera of the human eye reveals the direction of gaze, making it a tool for social communication. It also shows emotions and health. The sclera is covered by the conjunctiva, a thin membrane containing tiny blood vessels, certain emotions, such as fear or sadness, and certain pathologies, such as allergies and conjunctivitis, cause these vessels to dilate, making the sclera redden. Genes do not miss this. Photographs of faces with artificially reddened eyes appear emotional and less attractive. Liver disease and aging can give the sclera a yellowish tint. Whitening the sclera makes the face more attractive. Here's another subtle detail. In babies, the whites of the eyes are slightly bluish. With age, they gradually turn yellowish or become cloudy. That is why adding a hint of blue to the whites of the eyes in a portrait reliably makes a face look younger. And don't forget the sparkle. The sparkle in the eyes is not poetry, it's physics. Our eyes are covered with tear fluid. When you are young and healthy, this fluid is abundant, and light reflects beautifully, creating shine. With illness or age, the eyes dry out and become dull. Professional photographers know this and deliberately add highlights to make eyes look more attractive. Artists knew it centuries ago. The eyes of Vermeer's girl with a pearl earring are bright and lively, while the eyes of the Mona Lisa lack visible glare, which amplifies her mystery. In anime, eye highlights are exaggerated to maximize attractiveness, while filmmakers often remove glare from the eyes of villains to make them appear lifeless or unsettling. Even butterflies exploit this trick. Some species display fake eyes with painted highlights on their wings, deceiving predators and attracting mates. Evolution literally paints glare for survival. Another remarkable insight was proposed by William Hamilton. He realized that evolution does not care only about the individual. We share genes with our siblings, cousins, and offspring. That is why a gopher screams when it sees an eagle. It risks its own life, but saves its relatives, and with them, the shared genes. This is known as inclusive or cumulative fitness. Humans, too, unconsciously read signals of kinship, health, and age from faces, and the eyes play a crucial role in this process. Pupil size, moisture, sclera color, and overall clarity all transmit information. We think, we perceive beauty. In reality, we are evaluating probabilities, the likelihood that these genes will continue into the future. And this brings us to the central question. Do we perceive reality as it really is? We will find a paradoxical answer. If our senses have evolved and been shaped by natural selection, then space-time and physical objects, like beauty, are in the eye of the beholder. They inform us about fitness, not about truth or objective reality. We are used to trusting our eyes. It feels obvious. If we see a banana, then it exists. It is really there, greenish, smooth, cold to the touch. Scientists usually nod in agreement. Of course, evolution has taught us to see reality as it is. After all, accurate perception should be the key to survival. But let's entertain a disturbing thought. What if the opposite is true? What if natural selection does not reward truth at all? We tend to assume that seeing reality and being evolutionarily fit are the same thing, but they are not. Imagine a pile of manure. For us, it is filth and disease. For a dung fly, it is luxury, food, and a home. The reality is identical manure, yet its meaning for survival is completely opposite. Evolution does not care about truth. It cares about fitness points. Seeing what is true and seeing what is useful are two very different strategies, and they compete. This creates a paradox. If we do not perceive reality as it is, then what about science? DNA, neurons, atoms, these are also things we observe. If perception is deceptive, doesn't evolutionary theory collapse under its own logic? No. And here is why. There is a concept called universal Darwinism. Darwin's idea is not merely a biological theory, it is an abstract algorithm. Wherever there is variation, inheritance, and selection, it will operate. In biology, organisms compete. In language, words compete and disappear. In culture, melodies, ideas, and symbols fight for attention. Physicist Lee Smolin even suggested that this algorithm may apply to entire universes, where black holes give rise to new cosmic offspring with slightly different physical laws. This algorithm does not require space, time, or physical objects. It requires only mathematics, replication, variation, and selection. Philosopher Daniel Dennett called Darwin's idea a universal acid. It dissolves comforting intuitions and leaves only structure behind. Even if space and time turn out to be nothing more than an interface created by the brain, Darwin's algorithm still survives intact. It does not depend on what reality is. It depends on what wins. How can we know for sure who wins truth or utility? Game theory can help us here. Look at animals. Take scorpions, for example. They are aggressive creatures, ready to fight to the death at the slightest provocation. But there are others. Some snakes retract their fangs during fights. Deer clash only with their antlers and never kick each other in the stomach. Why does such apparent nobility exist in the wild? It has nothing to do with morality. It is pure calculation. Imagine a simple game. There are two strategies: hawk and dove. The hawk always attacks and escalates the conflict to the end. The dove retreats if attacked. If the reward for victory is high and the cost of injury is low, it is profitable to be a hawk. But if the cost of fighting is enormous severe injury or death, then a population made entirely of hawks will quickly destroy itself. In that case, being a dove becomes the winning strategy. The mathematics of this game shows something unsettling. The most aggressive or the most honest strategy does not always win. What matters is not virtue, but payoffs. The same logic applies to perception. We can mathematically calculate whether it is advantageous to see the world as it truly is. And the key lesson is simple. Survival depends not on objective strength or accuracy, but on context, on who surrounds you and what strategy they use. Now, let's apply this logic to vision and our perception of reality. We intuitively believe that evolution should reward organisms that see the truth. The more accurately you see the world, the better you survive. At least, that's what common sense tells us. To test this intuition, cognitive scientist Donald Hoffman, together with mathematician Chetan Prakash, formulated and rigorously proved a theorem they called fitness beats truth. The essence is simple. Imagine two beings. Let's call the first one truth. It sees the world as it really is. It knows exactly how much of a resource exists, say, oxygen. The second creature we'll call adaptability. It does not see objective reality at all. It sees only what is useful for survival. It does not perceive the amount of oxygen, but simple markers, safe or deadly. Who wins under natural selection? Mathematics gives a clear answer. Truth dies out. The probability that natural selection would tune our senses to perceive true reality is practically zero. For an eye even simpler than a human one, that probability is on the order of 1 in billions of billions. Why does this happen? Imagine a creature that depends on a certain resource. Too little of it and you die. Too much of it and you also die, as with oxygen or water. The relationship is a bell-shaped curve. Survival exists only in the middle. The creature called truth sees that there is more of the resource, but that knowledge alone is useless. Is more good or bad? Truth doesn't know. It has to calculate. Adaptability, on the other hand, sees only a signal: danger. It doesn't care whether the amount is large or small. It knows the only thing that matters: it must run. Adaptability expends less energy and makes faster decisions. Truth is too complex, too slow, and too inefficient. In the evolutionary race, it loses decisively. You might object, but we have big brains. We are designed to understand the truth. This, too, is a myth. Over the past 20,000 years, the human brain has actually shrunk. We have lost a volume roughly the size of a tennis ball. Biologically speaking, we are not becoming smarter. We have simply learned to survive inside social systems that insure us against error systems, where mistakes no longer immediately lead to death. Personally, all of this sounds disturbing. When you hear that evolution actively hides the truth from us, your first instinct is to look for an error in the math. Surely something must be wrong. Perhaps the models are too simplified. Perhaps Hoffman and his colleagues overlooked something fundamental. After all, nature is far more complex. Populations are finite. Random mutations occur. Organisms interact in intricate and nonlinear ways. Maybe if we add all these details, the outcome will change. Maybe, in a richer and more realistic model, truth will finally win. But the unsettling implication remains. Even when we make the models more complex, utility still dominates accuracy. Unfortunately, no. Mathematics is relentless. Consider a phenomenon known as neutral drift, a process in which random mutations spread without providing any survival advantage. In small populations, neutral drift can slow the extinction of truth. But slowing is not the same as saving. Natural selection continues to apply pressure, and that pressure is always directed against truth, trying to eliminate it. To test this, Donald Hoffman's student, Justin Mark, created a virtual world. He ran simulations spanning thousands of generations of digital organisms. The first generations were complete idiots. They crashed into walls and tried to eat empty space. But generation after generation, they improved. Eventually, they became masters of survival. And here is the key result. Not a single population evolved to see the truth. They evolved to see utility. But maybe, you might say, we need to simulate the entire Earth to be sure. No, we don't. Take the lottery. To understand that your chances of winning are negligible, you don't need the biographies of every ticket buyer. Probability theory is enough. The same logic applies here. The probability that evolution would accidentally tune our senses to the true structure of reality is astronomically close to zero. Truth has worse odds than a lottery ticket. Why do we need eyes if they lie? To answer this, let's return to the example from the beginning of the video. The yellow folder on your desktop is not actually yellow. In reality, it is a pattern of zeros and ones scattered across silicon. But the icon is not trying to deceive you. On the contrary, it helps you. If you had to control a computer by manipulating voltages and rewriting binary code, you would never send even a simple email. The interface hides the complexity so that you can act. This idea is known as the interface theory of perception. Evolution has done exactly the same thing to us. Space and time are our desktop. Physical objects, spoons, bananas, stars are icons. Nature does not want us to see quantum fields or vibrating strings. That would be useless and fatal. It wants us to survive and reproduce, so it gives us a simplified interface. We do not see reality. We see data structures optimized for survival. And now you might ask the obvious question. If a rattlesnake is just an icon, why shouldn't I pick it up? I won't grab a rattlesnake for the same reason that I won't carelessly drag a brush icon across my drawing. In a graphics application, not because I perceive the icon literally, there is no brush in my laptop, but because I take it seriously. I know that if I drag it across the screen, I will ruin my drawing. And that's the point. Evolution has shaped our senses to keep us alive. It's better to take them seriously. If you see fire, don't step into it. If you see poison ivy, don't eat it. If you see a rattlesnake, don't grab it. In other words, the snake is a warning sign in our interface, like a skull icon or a high voltage symbol. The icon itself doesn't kill you, but ignoring it will. This also explains mimicry in nature. Why does a harmless spider pretend to be bird droppings? It hacks the predator's interface. It's phishing, but in biology. Hackers fake bank logos to steal passwords. The spider fakes a feces icon so birds won't eat it. This is a war of interfaces, and we fall into the same trap constantly. We are so used to our interface to space and time that we start treating it as ultimate reality. We reify icons. We assume that when we look at the stars, they exist out there exactly as we perceive them. But what is reality, really? If you have a headache, is it real? Absolutely. But does that pain exist when you don't feel it? No. The same logic applies to objects. Neurons, atoms, stars, they are real as experiences. But believing that they exist in the same form without an observer is a mistake. Look at this molecule. Carbon, hydrogen, oxygen. What does it taste like? You'll say, vanilla. But do carbon atoms taste like vanilla? Of course not. Taste is an icon, a convenient label evolution attached to a chemical structure to tell us this is edible. If we had to analyze every atom before eating, we would starve. We consume icons, not equations. Sometimes these icons fail. Remember the Australian beetles mating with bottles. We laugh, but we also don't see quantum fields or atomic lattices. We see a trash icon, where the beetle sees a super female. Our perception isn't truer, it's just better adapted to this situation. But if everything we see is an interface, then how does science work? We cure diseases. We land rovers on Mars. So, do we see the truth after all? Imagine a Formula One champion. He feels the car perfectly. He takes turns at insane speeds and wins races. On the track, he's a god. But does he understand the thermodynamics of fuel combustion or the molecular structure of rubber? No, and he doesn't need to. Scientists and engineers are like elite drivers. They have mastered the rules of interaction within our interface well enough to build vaccines and spacecraft. But mastery of the interface is not the same as understanding what reality is made of underneath. Scientific theories expressed in the language of objects in space-time are theories that are still tied to the interface. They cannot adequately describe reality, just as theories expressed in the language of pixels and icons cannot adequately describe a computer. Some physicists, as we shall see, recognize this and conclude that space-time is doomed along with its objects. Einstein never stopped thinking about the meaning of quantum theory. We often discussed his thoughts on objective reality. I remember once, while we were walking, Einstein suddenly stopped. turned to me and asked if I really believed that the moon only existed when I looked at it. You know, we all live with a very strange belief. We assume that the world around us is solid, reliable, and the same for everyone. If I see the moon and you see the moon, then the moon must objectively exist. As the great physicist Wolfgang Pauli once remarked, arguing about whether the moon exists when no one looks at it is like counting angels on the head of a pin. Albert Einstein agreed. He believed in realism that physical objects have definite properties, such as position or spin, even when no one observes them. And he believed in locality, that nothing can influence anything else faster than light across empty space. But in 1964, John Bell proved that Einstein's worldview could not survive quantum mechanics. The theory predicted effects that simply should not exist in a local, realistic universe. Imagine two electrons that are entangled. Measure the spin of one, and you instantly know the spin of the other, even if it is on the opposite side of the universe. Experiments confirm this again and again. Electrons behave as if distance does not exist for them, as if they have no definite properties until the moment of measurement. This strikes at the heart of common sense. Either reality is not local, or it is not real in the way we intuitively believe. Nobel Prize-winning physicist Anton Zeilinger conducted a series of decisive experiments and came to a radical conclusion. We will most likely have to abandon realism itself. Physical properties do not exist until we ask nature a question. The Kochen-Specker theorem goes even further. It shows that the value of a property depends on how you measure it. There is no such thing as spin in itself. There is only spin in the context of this specific experiment. It's like mood. You don't have a mood in itself. Your mood depends on who asks you, when they ask, and how. Carlo Rovelli, another brilliant physicist, says directly, "I try not to change quantum mechanics to fit my view of the world, but to change my view of the world to fit quantum mechanics." According to Carlo Rovelli, all properties are relative. The state of a system does not exist by itself. It exists only in relation to an observer. Reality, in this view, is not a collection of objective facts, but a web of relationships. Think about the famous double-slit experiment. We fire a single photon at a screen with two slits. If we monitor which slit it passes through, the photon behaves like a particle. It goes either left or right. But if we do not observe it, the photon behaves like a wave and passes through both slits at once. That alone already sounds insane. The particle seems to know whether we are watching it. But John Archibald Wheeler proposed something even more disturbing: the delayed choice experiment. The idea is simple and terrifying. We let the photon pass through the slits first, and only after that do we decide how to measure it and what happens. If we choose to measure its path, it turns out that in the past, the photon behaved like a particle. If we choose not to measure the path, we discover that in the past, it behaved like a wave. Our present choice appears to determine the particle's past. Cause and effect run backward. Wheeler then scaled this idea up to the size of the universe. Look at this image. A distant quasar, a supermassive black hole shining brighter than hundreds of galaxies. Its light has been traveling toward us for 8 billion years. Along the way, it bends around a massive galaxy that acts as a gravitational lens, splitting the light into multiple paths. This object is known as Einstein Cross. A photon from that quasar has already completed an 8 billion year journey. And yet, when it finally reaches our telescope today, we can still choose how to measure it. If we ask which path it took, the photon acquires a single, well-defined history. If we measure interference instead, it turns out that for 8 billion years, the photon traveled along all possible paths at once. Sitting here and now, by making a choice, we seem to rewrite a history that unfolded long before the Earth even existed. Our choice today determines billions of years of history. Most of us cannot lift 100 kilograms, but we can reach back trillions of kilometers and billions of years to rewrite the past. A feat worthy of Hercules. This raises the stakes. Quantum theory shatters our intuitive ideas about objects, denying that they have definite values and physical parameters that do not depend on whether and how they are observed. Now, it shatters space and time. There is no space. There is no time. The word time is not sent down from above. It was invented by man. If there are problems with the concept of time, we created them ourselves. As Einstein said, space and time are principles of our life. Thinking, not conditions in which we live. Albert Einstein gave us a beautiful idea. He fused space and time into a single entity space-time, and for a moment, it felt as if we had finally touched bedrock reality. Something solid, something fundamental. But then came John Archibald Wheeler, and he shattered that illusion. Wheeler argued that space and time are not fundamental at all. They are not the bottom layer of reality. At the deepest level, he said, lies information. He called this principle it from bit. Everything we perceive as matter ultimately arises from immaterial bits of information. Our intuition rebels against this. It feels obvious that space must come first, and information is merely stored inside it. But intuition fails us again. Imagine you are designing memory for a supercomputer. Your goal is to pack as much information as possible into the smallest space. Your competitor uses 6 small spheres and fills them with data. You laugh and choose one huge sphere that easily contains all 6 smaller ones with room to spare. Clearly, you think your solution should store more information, but you are wrong. Jacob Bekenstein and Stephen Hawking discovered a deeply counterintuitive law. The maximum amount of information that can be stored in a region of space depends not on its volume, but on the area of its surface. Your giant sphere has less surface area than the combined surface of 6 smaller spheres and therefore holds less information. This insight became known as the holographic principle. Space-time, it turns out, is not smooth. It is granular, pixelated, with the smallest possible unit, the Planck length. Hawking realized that the total number of bits in any region of the universe is limited by how many of these fundamental pixels fit on its boundary. Reality, then, is like a computer game. It looks three-dimensional and deep, but all the information is encoded on a flat, two-dimensional screen. Leonard Susskind and Gerard Hooft confirmed this picture. Galaxies, stars, planets, you and me are holograms. We appear three-dimensional, but everything that defines us is written on a distant two-dimensional boundary. And as if that weren't enough, black holes delivered one final shock. Hawking showed that they are not eternal. They radiate energy, shrink, and eventually evaporate, threatening to tear the foundations of physics apart. Imagine you jump into a supermassive black hole. According to Albert Einstein and his general theory of relativity, you would cross the event horizon without noticing anything special, at least not until gravity eventually stretches you into spaghetti. The crucial point is that all information about you would be trapped inside. The details of your death would remain sealed beyond the horizon. Now, fast forward trillions of years. The black hole evaporates. Where did that information go? It vanished forever. And here, the paradox explodes. Quantum mechanics, the foundation of all modern physics, insists that information can never be destroyed. Remove this rule, and the theory collapses. But relativity seems to say the opposite. Black holes erase information when they evaporate. The two pillars of physics are in direct conflict. One says information is eternal. The other says it can disappear. One of them must be wrong, and this is one of the deepest cracks in our understanding of reality. To expose it, physicists invented a thought experiment starring Alice and Bob, legendary explorers of theoretical paradoxes. Alice heads toward the supermassive black hole at the center of the Milky Way. She carries a box containing a single electron with a fixed spin, a qubit, a unit of quantum information. Bob stays behind to observe. Alice steps into the abyss and tosses the box slightly ahead of her. From Bob's perspective, something strange happens. As Alice approaches the event horizon, gravitational time dilation slows her down. She never quite crosses. Her image reddens, fades, and freezes at the edge. To Bob, Alice and the box smear across the horizon and dissolve into darkness. But Bob trusts quantum mechanics. Information cannot vanish. So he waits. He builds a colossal detector around the black hole to capture every particle of Hawking radiation. He uploads his consciousness into a machine and waits out the death of the stars. Trillions of years pass. The universe cools. The black hole evaporates. And finally, buried in the radiation, Bob finds patterns. He reconstructs the information. He recovers Alice. And what does that information say? It says that Alice felt nothing unusual. According to Einstein's equivalence principle, free fall is indistinguishable from weightlessness. The black hole was so massive that tidal forces were negligible. No stretching, no freezing, no wall at the horizon. Alice saw darkness ahead. She saw the box with the electron drifting in front of her. The box crossed the event horizon, and Alice followed it. From her perspective, both she and the electron pass the point of no return without incident. But now comes the impossible question: where is the electron? Bob, standing outside the black hole, is holding that same electron in his hands. He reconstructed it from the radiation. For Bob, the electron never fell and it remained encoded on the event horizon. For Alice, the electron was inside the black hole with her. One electron, two locations, two equally valid descriptions. Both consistent, both true, and they cannot be combined into a single picture of reality. There is a fundamental law of physics known as the no-cloning theorem. Quantum information cannot be copied. There cannot be two identical electrons in two different places at the same time that would violate unitarity. And here we hit a wall. Either Bob is wrong or Alice is wrong. Their realities contradict each other. This paradox haunted physicist Leonard Susskind for years, until he proposed a radical escape: the principle of complementarity. The idea is unsettling, but precise. There is no God's eye view of reality that sees everything at once. There is only the perspective of a specific observer. For Bob, Alice was flattened and encoded on the event horizon. For Alice, she crossed the horizon effortlessly and was destroyed only later. Both descriptions are true, but never simultaneously accessible. The key is that Alice and Bob can never meet to compare notes. Alice cannot send a message back out. No observer can witness both stories at once. And as long as no one can see both pictures simultaneously, there is no contradiction. The complementarity of the horizon seems radical, but it works. It allows quantum theory and general relativity to coexist without contradiction. But we must abandon the idea that we can describe space-time and objects outside the horizon and simultaneously inside the horizon. The assumption that we can see both is the problem. If we abandon the divine eye from nowhere, then quantum theory and general relativity can coexist peacefully. We are forced to abandon the idea that there is one objective space-time for everyone. The space inside the whole and outside are different, complementary realities. By letting go of the idea of a single space, we save physics and reconcile Einstein with quantum mechanics. Physicists like Raphael Bousso now talk about causal bubbles. Each of us has our own personal bubble of reality. You have your bubble, I have mine, but we cannot sew them into a single, consistent fabric. Reality differs for different agents. This is not as strange as it may seem. What is real for one agent is based entirely on the experience of that agent, and different agents have different experiences. If I see one thing and you see another, as in the case of a black hole, that's not a problem. Contradictions arise only when we try to draw a single map that must be true for everyone at once. And such a map simply does not exist. There is no unique, objective spacetime shared by all observers. There are countless descriptions of reality, each valid only relative to a particular observer. You might object, fine. But what about the Big Bang? It happened 13.8 billion years ago, long before any observers existed. That must be an objective fact. And here, Stephen Hawking gives a deeply unsettling answer. He proposed what he called top-down cosmology. We usually imagine a fixed past. First, the Big Bang, then galaxies, then stars, then us. Hawking argued the opposite. The early universe was quantum and fuzzy. It did not have a single, well-defined history. It existed as a cloud of probabilities. Only now, when we look through telescopes and ask questions about the past, do we select one specific history out of many. Our measurements today do not merely reveal the past, they help determine what the Big Bang was. The history of the universe depends on what is observed, contrary to the common idea that the universe has a unique history, independent of the observer. In our past, there is an era of the early universe when quantum gravity was important. The remnants of this early phase are all around us. The central problem of cosmology is to understand why these remnants are what they are and how the distinctive characteristics of our universe emerged from the Big Bang. If one takes a bottom-up approach to cosmology, it immediately leads to what is essentially a classical framework in which it loses the ability to explain the central question of cosmology, why our universe is the way it is. Thus, the basis we propose is more of a top-down approach to cosmology, where the histories of the universe depend on the accuracy of the questions asked. Once again, Hawking and a number of other physicists say this. The history of the universe depends on what questions we ask it today. when we measure the expansion rate of the cosmos or the energy of the vacuum. Right now, we are cutting off all the past possibilities that do not lead to this result. Remember the quasar experiment? Our choice to measure a photon today determines which path it took billions of years ago. John Wheeler looked at this and asked, isn't the Big Bang simply the sum of all acts of observation? Every elementary quantum phenomenon is an elementary act of creating a fact. This is indisputable. But is this mechanism the only one necessary to create all this? Is what happened during the Big Bang a consequence of billions and billions of these elementary processes, these elementary acts of observer participation, these quantum phenomena? Has the mechanism of creation been before our eyes all this time, and we did not understand the truth? The approaches of Stephen Hawking and John Archibald Wheeler are fully consistent with what is sometimes called cubist or cubist cosmology. In this view, a quantum state is not a description of an objective thing out there. It is a description of my confidence as an observer. The past, including the Big Bang, is not a frozen monument carved into reality. It is a construction we continuously assemble based on what we observe today. As physicist Christopher Fuchs puts it, the Big Bang is not a distant event locked 13.8 billion years ago, but an ongoing process of creation in which we all participate. We began this journey with Donald Hoffman's radical prediction. Space-time and physical objects do not exist outside perception. They are not fundamental. And remarkably, modern physics does not contradict this claim. On the contrary, it lends its striking support. Yes, we have not discussed other interpretations of quantum mechanics, de Broglie-Bohm, Everett's many worlds, and others which try to preserve an objective space-time filled with things. We simply don't have time. Otherwise, this video would run for 2 hours. What matters is this: the interface theory of perception is not fringe or forbidden. Its key prediction that space-time itself is doomed as a fundamental concept is moving dangerously close to consensus among physicists. For example, Nima Arkani-Hamed, during a lecture at the Institute for Theoretical Physics, noted, "Almost all of us believe that space-time does not exist, that space-time is doomed and must be replaced by some more elementary building blocks. If space-time is doomed, then physical objects are also doomed. Their place must be taken by more elementary building blocks. But if space-time is not the cornerstone of reality, not a pre-existing stage for the drama of life, then what is it? I believe it is a data-compressing and error-correcting code for fitness. Many of the world's leading physicists, David Gross, Edward Witten, Nima Arkani-Hamed, arrive at the same unsettling conclusion. Space-time is doomed. It is not fundamental. In a final description of nature, there will be no meters and no seconds. They will vanish, giving way to something deeper and more abstract. For physics, this is not a catastrophe, but a challenge. It means we are finally beginning to understand what the discipline is really about. But here is the problem. While physicists are quietly burying space, our brains stubbornly insist that it is real. We see objects, shapes, distances, motion. Why do we perceive something that, at the most fundamental level, does not exist? The answer lies in evolution. Our task was never to know the truth, only to survive. Reality is absurdly complex. If the brain attempted to process every quantum fluctuation, every field, every hidden dimension, we would freeze like an ancient computer and a lion would eat us. Data compression is not optional. It is a matter of life and death. Vision performs exactly this function. It compresses an unimaginably complex, high-dimensional reality into a usable format, 3-dimensional space and time. We do not see the world itself. We see an archive of the world. We don't perceive the countless particles passing through our bodies every second. We perceive just enough to dodge a stone. But compression alone is not enough. There must also be error correction. When digital data is transmitted, redundancy is added so mistakes can be detected and fixed. Without it, modern civilization would collapse. Our senses work the same way. A perceptual error is fatal. Misjudge the distance to a predator, and you die. That is why evolution built redundancy into our interface. And this is where physics and biology unexpectedly meet. Recall the holographic principle. All information inside a volume is encoded on its boundary. Physicists such as Ahmed Amheri have shown that this extra dimension of space behaves like an error, correcting code in a quantum computer. Space is not an empty container. It is a protective code, a mechanism that preserves information against destruction. There are many clever ways to add redundancy, such as embedding messages in higher dimensional spaces. But the key point is that our senses convey messages about fitness benefits, and getting the message right is critical for survival. Get the order of magnitude wrong in terms of fitness, and you can kiss your life goodbye. It is entirely reasonable to expect that natural selection has built redundancy into our perception interface. This is precisely what Bekenstein and Hawking discovered. About space-time, it is redundant. In any three-dimensional space, all information is contained in two dimensions. This is the universally accepted holographic principle. It is counterintuitive and contradicts our assumption that three-dimensional space is an objective reality that is reproduced by our senses. But it makes sense if we assume that our senses report on fitness and need redundancy to ensure that their reports are not corrupted by noise. Let's take a simpler example. Why do we see so much symmetry? Butterflies, lions, apples. Our bodies, after all, they are all symmetrical. Old school scientists say we see symmetry because the world is symmetrical. But the fictional symmetry theorem, formulated by Hoffman and proven by Chetan Prakash, says no. The symmetry you see with your eyes says nothing about reality. So why do we see symmetry? Again, for economy. To remember the shape of a banana, the brain doesn't need to store every pixel. It's enough to remember half of it, and the rule, mirror it. Symmetry is a compression trick. It's an algorithm that allows the brain to store less data. And here, you may object. Wait a minute. We know how to build computer vision systems. These systems control machines and see the same shapes and symmetry that we do. Doesn't that mean that we and computers see reality as it is? Not at all. The theorem of fictitious symmetry applies to any perception system, biological or machine. The symmetry that a computer sees tells us nothing about the structure of objective reality. We can create a robot that sees the symmetry that we see, but that does not give us any insight into the structure of the world. To plan and act, we don't need truth. We need an interface. Look at players in GTA. They steal cars, rob stores, coordinate complex raids, and plan flawlessly. But do they see reality? Of course not. The real reality of the game is silicon chips, electrical voltages, and millions of lines of code. If a player suddenly saw only zeros and ones, the game would instantly become unplayable. What the player sees instead is the interface, streets, cars, people, and that is more than enough. Perception must be economical. Seeing everything is too expensive for the brain. That's why we compress data and, crucially, correct errors in real time. Twilight. You're walking through a garden and suddenly you see a snake. You jump back. Your heart explodes in your chest. A second later, you realize it's just a garden hose. Were you wrong? Yes, but it was a useful mistake. Your system sent an immediate, unchecked signal. Danger, because it's far better to waste a few calories being afraid of a hose than to miss a real viper and die. Evolution rewards paranoia, not accuracy. Your brain is constantly filling in the picture of the world, repairing gaps, and correcting corrupted signals. Take a simple illusion, two circles with missing segments. Rotate them in just the right way, and you suddenly see a line between them. But there is no line. Your brain simply decides, there should be something here. The signal must have been erased. I'll restore it. And so you perceive something that does not exist. We do not live in an objective world. We live inside an interface woven from useful simplifications, compressed data, and constant error correction. And that is the only reason you are still alive. Oscar Wilde once wrote that pure color whispers 1,000 things to the soul. He was right, though he probably wasn't thinking about evolution. Color is information. A red traffic light, green grass, a bruise on your knee. These are survival signals. But here's the trap. Try to imagine a color you've never seen. You can't. Neither can I. We are locked inside a narrow palette, like prisoners behind invisible walls. The electromagnetic spectrum is vast, but we see only a thin slice from about 400 to 700 nanometers. X-rays, ultraviolet, microwaves, all of it is invisible. And even within this tiny window, we compress mercilessly. Millions of receptors send data to the brain, and the brain keeps only a rough summary. Color is not just a wavelength. It is also an image that triggers feelings and actions. Psychologists try to compile dictionaries of these signals. Red means power or hunger. Blue means competence. White means sincerity. But this is far too crude. Everything depends on context. Take brown. On a hat, it may look intelligent and prestigious. Show the exact same shade on a random surface, and people will call it dirty and unpleasant. The pixels hitting the retina are identical, but the brain, depending on the situation, produces completely different emotions. Culture reshapes this code as well. Spaniards see pride and passion in the red of bullfighting. People with chromophobia may feel panic at the same color. Color is not in the world. It is in the interface. What's even more astonishing is that humans are not the only ones who speak this language. Plants see, too, despite having no eyes. They actively hunt for light. Their sprouts search for blue photons to know where to grow, and red light works for them like a clock. Catch a red photon, it's morning. Catch far red, it's dusk. This is how plants measure night length and decide when to bloom. Some organisms have pushed this ability far beyond us. There is a tiny cyanobacterium that has lived on Earth for billions of years. It uses its entire cell as a lens and possesses up to 27 types of photoreceptors. Compared to it, we are almost blind. Yes, we can distinguish millions of colors, and that alone is miraculous. But something even more powerful than color exists. It is the combination of color and texture. Scientists call this chromatography. Take green. If it's green, bumpy broccoli, you enjoy it. Put the same green on a piece of meat and you feel disgust. Chromatography is a compressed instruction set for action. A glossy surface whispers, "Touch me." A prickly one says, "Danger." A fluffy texture invites you to hug it. This is an incredibly dense stream of information, far richer than simple color labels. A tiny fragment of an image can carry more actionable data than there are stars in the universe. Chimpanzees read fruit this way, combining color and bumps to judge ripeness. Fake the texture, and the monkey is fooled. We are built the same way. Red blood triggers fear. Red strawberries trigger appetite. This code controls our emotions. And the hardest truth to accept is this: we do not see objective reality. We assume everyone sees the same world. When I say the tomato is red, you nod. But that does not mean we see the same thing, not even close. There are amazing people called synesthetes. They make up about 4% of the population. They live in a completely different reality. For example, in his book Speak, Memory, writer Vladimir Nabokov describes his own color hearing. Synesthete Michael Watson described his experience of eating mint as follows: "I feel a round shape. It is also very cold. So it must be some kind of glass or stone, judging by the temperature. The most amazing thing is its absolute smoothness. The only thing I can compare this sensation to is touching a tall, smooth glass column." And artist Carol Steen sees music, for her notes are falling golden balls or colored lines. Her synesthesia exudes a stream of creative imagery from which she draws inspiration for her paintings and sculptures. These brilliantly colored and dynamic images, or photisms, instantaneous and vivid. Scientists have discovered that synesthesia is hereditary. The genes associated with it are located on specific chromosomes. In simple terms, synesthetic brains have more cross-connections between different neural regions. Areas responsible for color are directly wired to areas responsible for letters, numbers, or sounds. What most people experience as strictly separated channels are, for synesthetes, fused into a single interface. This gives them real advantages. Synesthetes often possess extraordinary memory. A famous example is Daniel Tammet, who used color number associations to memorize more than 20,000 digits of pi. And he is far from unique. There are many such cases. The key point is this: synesthesia is not a defect. It is simply a different interface, one that, in certain tasks, outperforms the standard human model. So what can we conclude? Evolution is an endless hacker. It never stops experimenting with interfaces. We have one. Bats with echolocation have another. Mantis shrimp, which see ultraviolet light and polarization, have a third. None of these interfaces is true. There is no perfect way to see the world. There is only the way that helps genes survive and replicate. Perhaps someone like Michael Watson, who experiences flavors as shapes, has an interface superior to ours. If survival depended on haute cuisine, natural selection would have chosen him over us without hesitation. Evolution is not done tinkering with the sensory interfaces of Homo sapiens, mutations that make 1 in 25 people happy. with some form of synesthesia, are certainly part of this process, and some of these mutations may become established. Most of the improvements are aimed at our perception of colors. Evolution pays no attention to the silly constraint that our perception must be accurate. It freely explores infinite forms of sensory interfaces, occasionally stumbling upon new ways to direct our endless hunt for fitness. Every second, a tsunami of information, billions of bits of data crashes into your retina. You have around 130 million photoreceptors, and every single one is screaming something at your brain. If all of this were processed directly, you'd get a cognitive blue screen of death right in the maternity ward. Luckily, we are equipped with a powerful spam filter. First, the eye brutally compresses the image, discarding almost everything. Then, attention steps in. Out of billions of incoming bits, only about 40 reach consciousness. Think about that. Billions in, 40 out. We believe we see the world clearly, edge to edge, but that's an illusion. In reality, sharp vision occupies a tiny patch, about the size of a thumbnail at arm's length. Everything else is blur. Our eyes constantly jump around, sampling fragments, and the brain stitches them into a seamless picture. This ruthless economy of resources produces a strange side effect: change blindness. If you are shown 2 photos of a city where an entire building has vanished, chances are you won't notice. Your brain has already tagged that part of the scene as irrelevant and refused to waste attention on it. We don't see everything. We see only what matters for action. So what then is the objective world actually made of? The honest answer is simple: we don't know. Scientists propose different frameworks. What follows is a condensed version of the ideas of Donald Hoffman. One popular hypothesis is that we live in a computer simulation. We are avatars in someone else's game. The Sims, the Matrix, pick your metaphor. Somewhere, a programmer runs the code. Or maybe that programmer is himself inside another simulation. Thinkers like Nick Bostrom, David Chalmers, and Elon Musk do not dismiss this possibility. Our space-time does look suspiciously like a pixelated screen, but there is a fatal hole in this idea. How does computer code turn into feeling? How do zeros and ones become the taste of morning coffee or the smell of rain after a storm? No one knows. We can't even imagine how to write a program that feels. Saying it's a simulation simply pushes the mystery of consciousness one level higher. It doesn't solve it. We know neurons are correlated with consciousness, but how exactly? Psychologist and Harvard professor Steven Pinker believes that we may never solve this problem at all. We may have hit a wall, and this is where the good old principle of Occam's razor becomes useful. It says, choose the simplest explanation. Scientists traditionally prefer monism, the idea that reality consists of a single substance. Physicists usually claim everything is made of matter, which exists as particles and fields, and consciousness is merely a byproduct. But modern physics increasingly suggests that space and time themselves are not fundamental, they are just a stage, a backdrop. And yet, we stubbornly continue trying to explain consciousness as something that emerges from neurons and atoms, even though those very atoms and space-time may not be fundamental at all. Scientists have tried everything. Roger Penrose searches for consciousness in quantum processes inside cells. Giulio Tononi builds elaborate theories of information integration. But none of these approaches can answer a brutally simple question. What is the formula that produces the smell of pine or the taste of coffee? They are trying to pull a rabbit out of a hat, but the hat is empty. Matter does not explain experience. So what if we apply Occam's razor differently? What if the foundation of reality is not matter at all, but consciousness itself? Donald Hoffman calls this idea conscious realism. What does all this mean for us today? For example, how does artificial intelligence look through Hoffman's lens? Right now, we assume that if we assemble enough chips and write sufficiently complex code, consciousness will eventually emerge on its own. But there is another perspective. A computer will not become conscious by itself, just as a stone will not suddenly start to think. However, we may create AI that functions as a portal. Just as a telescope revealed stars that were always there but invisible to the naked eye, sufficiently complex artificial intelligence could open access to forms of consciousness that we are currently unable to perceive. The theory of conscious realism also radically reshapes our idea of God. If conscious agents can combine into ever more complex structures, then mathematics allows us to describe an infinite conscious agent. This points toward a kind of scientific theology, not based on mysticism or superstition, but on formal models models and testable principles. Now, a few words about death. Imagine that you and a friend are wearing VR headsets and playing Mortal Kombat. You see each other's avatars, trees, a lake. Then you say, "I'm thirsty, I'll be right back," and remove the headset. Your avatar collapses. It stops moving. From inside the game, it looks dead. But are you dead? Of course not. You simply exited the interface. Perhaps death works the same way. Perhaps it is the moment when we take off the helmet of space-time when the interface shuts down. But the agent itself does not disappear. Donald Hoffman is often accused of returning humanity to the center of the universe, as if undoing the lesson of Nicolaus Copernicus and declaring once again that everything revolves around us. But this is a misunderstanding. Hoffman does not claim that humans are the center of reality. He claims that consciousness is fundamental, and human consciousness is only one instance among countless others. We are not special because we are human. We are special only in the trivial sense that we are the particular agents through which reality is currently being experienced. What is space-time? I offer you a red pill. Space-time is your virtual reality, a helmet created by you. The objects you see are your invention. You create them with a glance and destroy them with a blink. You have worn this helmet all your life. What will happen if you take it off?